We have done so far in this unit on exponentials and logarithms. We've talked about the bases, we've done some change of bases, we've graphed them, we've done a whole bunch of stuff, but now we're going to get to solving these types of equations. So we've graphed it, we've looked at it, we've transformed it, all of those things, we've talked about properties, and now we get to actually solve these kinds of equations. So our goal here is to find an x equals 2's number. So we're solving, finding a solution. There are a bunch of options for how these problems can be presented to you. They can either be really easy or medium. None of them I would consider to be difficult. The first types of equations we're going to be solving are exponential functions. So remember, for exponential functions, our x is in the exponent, which means we're just trying to figure out what that x is equal to. The first type of option you can have for an exponential function is if there is an x on both sides, meaning that you have a base and a base on both sides of the equation, and that there's a variable in the top of both of them. Usually they'll be the same variable. I know it says x and y, but it's just trying to prove a point to you. When that's true, and when the bases match, all you have to do is make the exponents equal to each other, and it really doesn't get more complicated than that. So if you look at this first example, notice that there's an x on both sides, but look at these bases. Aren't they both 5? Which really means all we have to do is solve the following: 3x equal to x minus 4. We just make the exponents equal to each other since the bases are equal to each other. Well, that's a good old-fashioned solving equations. To do this, we're going to subtract x from both sides so that this x goes away. We would then have 2x equal to negative 4. And I'm just using my good old-fashioned solving skills. What's the last step? By 2. And I do that on both sides. These 2's are going to cancel each other out. I have x equal to negative 2. Amazing, I'm already done. So these are level 1 problems where the bases already match. Does that make sense how I did that? You just took the exponents, you made them equal to each other, and solved. Let's make sure for ourselves that we know what's going on. Number 2 is for you. It's the same kind of problem, but I want you to solve it. Essentially, yeah, if the bases are the same, it's not that you're not using them, you're using them, but it's so easy to use them that it feels like they're not there. Say again? Not even at all. It's just because if they match, then everything about it has to be equal, which means these exponents have to be equal. So we would set up an equation x minus 3 equal to negative 2x plus 15. Since those are the exponents and the bases are already equal, the exponents have to be equal.
Also, if the bases are the same, you just solve the exponents.
Yeah. Which is why you can pretend like they're not there, but you're using them by pretending. We know they're equal. We know they match. Okay, I'll leave you here. I want you to finish it. So if I was going to solve this one, again, I like to move all of the x's to the left side, so that's what I'm going to do first. Plus 2x plus 2x. Obviously, the x's have to line up because they're like terms. So then I have 3x minus 3 equal to 15. Now, all of the regular numbers need to go to the right side, so I'm going to do plus 3 on both sides. Obviously, 15 and 3 are like terms because they're just plain numbers. So we'll have 3x equal to 18. And then when I divide by 3 to undo the multiplication by 3, I would get that x is equal to 6. After you utilize the idea of matching bases, it's an Algebra 1 style question where you're solving for x. So we got to utilize those skills that are in our brain somewhere. How did we do on that one? If I didn't give you enough time, were you headed the right direction at least? Okay. Now, what happens if the bases don't match? Are those bases the same? No, one base is 100, one base is 10. Yikes. They need to match for me to be able to do the matching exponents. Is there some way we could make one of these numbers change to become one of the other numbers? How are 10 and 100 related?
100 can be made 10
10 times 10. Oh, so like 10 squared, right? So what if I were to change the 100 to 10 squared? Is that still 100? Okay, then I'm just going to rewrite the rest of this problem. Oh, guess what now? The bases match. However, you multiplied all of the exponent of the 100 by 2. So we need to make sure that we actually use that exponent when we do the equals part. So I wouldn't just say x equals, I would say 2x equals negative x plus 3. Because I had to multiply all of that by 2 to get it to be 10 squared instead of 100. If we continued to solve this, I would add x to both sides to get that minus x to go away. This would be 3x equal to 3. Simple solving, we divide by 3, so that we get x is equal to 1. Okay, this next one I normally let you do and you do, but I want to hang on to you guys for this one, just because that changing of base thing was interesting. On number 4, when we first look at the problem, are the bases the same? No. Is there a way we can make one of the numbers into the other number, though? Yeah, how? We would have to add an exponent. Obviously, 2 is the smaller one, right? Let's work with 2. What is 2 squared? 4. Not 8, okay. What is 2 to the third power? 8. Isn't that what we wanted? 8. So what that means for me is I can rewrite this as 2 with the same exact exponent equal to the base of 2 if I multiply it by an exponent of 3 times that original exponent. Because 2 to the third power is 8. So I can raise that exponent to the third power and get it to be the same bases. Now the reason I wanted to hold on to you for this one is because, especially the way I've written it, do you have any sense of what I'm going to need to do with this 3 and this little term right here? You got a number in front of parentheses. What do we do? Distribute. So when I do this problem, I'm going to do 2 things at once. Once I start trying to set the exponent, or the, exponents equal to each other, I'm also going to distribute. Which means this is 3x plus 9. We solve for x by subtracting 3x from both sides, which would give me just 1x minus 2 equal to 9. What's the next step? Add 2 to both sides. Very good. So that we end up getting x is equal to 11. So the trick with these is the very easy problems where the bases match, like numbers 1 and number 2. You just set the exponents equal to each other and solve. But if they don't match, you have to figure out a way to make them match. Sound good? Okay, so that's the first type of exponential we might be solving. That's when there is an x on both sides, bases on both sides essentially. But what if there's only an x on one side? If there's only an x on one side, we're going to use the log loop that we did when we learned about the properties to rewrite it into a logarithm form and be able to type it in our calculator using the change of base formula. This one is actually more complicated, but somehow easier. So if I look at this one, I see that there is an x on only one side. The way that we solve this is we use the log loop. Log loop means I write the word log and I put the base. What is the base? 2. So that's going to be the little base number. The log loop tells me to literally just loop the other 2 numbers. So what number should we go next to the word log? 7. And what should that be equal to? X. Oh, snap, weren't we trying to find a value for x anyways? We wanted it to say x equals? Amazing. All we'd have to do is figure out what log base 2 of 7 is. Now, unfortunately, our calculator doesn't have a button for log base 2's. It only has a button for common logarithms and natural logarithms. But last class, we learned about the change of base formula, which we can use now to find the value of x. We would say that x is going to be equal to the log of 7 divided by the log of 2. That's the change of base formula, and that's something we can type in our calculator. Do y'all remember doing this last class? Yeah, so at this point, we just turned to our calculator. This is no longer things we can do in our head. I can't do these sort of things in my head. But we do log 7 close parentheses divided by log 2 close parentheses. And when we do that in our calculator, we're going to continue to round to the thousandths place, which is 3 decimals, unless you're told otherwise, which means x is going to be approximately 2.807. Now, as a review, why did I change my equal sign from being like a straight equal sign to a squiggly equal sign? Because it's approximately. I had to round that number, so technically we should be writing the squiggly equal signs. So see how this is technically more complicated because we had to use a logarithm to solve it, but like that was way easier, I think. Yeah? Let's see if you got it. I want you guys to try number 6. Yeah, you got it. Start with the log loop. Base never changes. It goes with the loop. If I were starting this one, I would first try to notice what the base is. The base is 3. Base never changes, which means this is going to be log with a base of 3. Woohoo! Then I have to loop it. Now remember, anything gets to be looped. Anything that's there, which means the big number that goes next to log should be the number 5, and that should be equal to the entire thing that was the exponent, x plus 3. Okay, cool. Well, log base 3 of 5 is going to be some number, right? Let's figure out what that is. So I'm going to rewrite this, putting my x first just because that's my habit, equal to the log of 5 over the log of 3. That's just the change of base again. And yes, I flipped it from side to side. I just like the x's being on the left. Well, I turned to my calculator and asked my calculator what log of 5, close parentheses, divide by log of 3 is, close parentheses. And my calculator would tell me that that is approximately 1.465. However, that is x plus 3. Do we want to know what x plus 3 is, or do we want to know what x is? Okay, how do I get rid of that plus 3? Not add, subtract it. Okay. Well, your calculator still has that number typed in, so just press -3. When you do that, your calculator is going to tell you that x is approximately negative 1.535. So if your question does require a little bit of algebra, we do have those skills still available. Don't forget the skills you've learned before. They're going to keep showing back up. Okay, so on this page, we learned how to solve exponentials. We learned how to solve exponentials when there was a value on both sides and when there was a value only on one side. The thing is, it has a partner type of equation of a logarithm, and we need to be able to solve those logarithms as well. So on the inside here, we're going to learn the 2 variations of solving logarithms. The first time is if there's a logarithm on both sides, kind of like the other side. So these are going to look like this, and it's the same exact rule. If the bases match, then the values are equal. Meaning the stuff in the argument, in the parentheses, we just set equal to each other, the same way we did the exponent a second ago. So if we look at this problem number 7, it says natural log of 4x minus 7 equal to natural log of x plus 5. Review question, what's the base of a natural log? Ooh, that's a common logarithm. E, the number E, weird, the number E. Cool, so the bases are the same, right? Because it's a natural log on both sides. So if the bases are the same, which they are because these are both natural logs, then all I have to do is set the parentheses stuff equal to each other. Same way I did on the front page. If we solve for x here, we're going to add, I'll do the x's first. We're going to subtract x from both sides so that I end up with 3x minus 7 equal to 5. And then I'm going to add 7 to both sides. That'll be 3x equal to 12. And then I divide by 3 to find out that x is equal to 4. Now here's the deal, and I tried to put this up at the top of your paper so that you could see it when you're looking at how to do this. What does it say right here? It says check greater than 0. What I mean by that is we're going to have to double check that each of the arguments, the parentheses in your problem, are not broken because those arguments have to be greater than 0. So to do that, we take the number 4 that we got as the solution and we plug it into the arguments themselves. I'm meaning these stuff in parentheses. We have to double check. What is 4 times 4 minus 7? Is that greater than 0? Well, 4 times 4 is 16, and 16 minus 7 is 9. Is 9 greater than 0? Yeah, so this one is okay. But we have to check both arguments to make sure that that value is okay. So then I also check if 4 plus 5 is greater than 0, which again, 4 plus 5 gives me 9. Is 9 greater than 0? Yes. So we have checked this one, and it's okay. So just like we did with like our square roots, where we had to check for extraneous solutions, logarithms potentially have extraneous solutions as well. Not exponentials, but logarithms. It has to do with the restriction in the domain. Can you guys try number 8 for me? I want you to find the value of x and check to make sure that it's not extraneous. So when we do this one, we notice again that these common logarithms have the same base, it's 10. So we can take the arguments, the parentheses, and set them equal to each other. Beep, 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 we solve the way we've been solving since 8th grade in Algebra 1, and we get the value 3. Cool, great, awesome. However, we have to check for logarithms to make sure that the parentheses are greater than 0. Now you can do that without showing as much work as I did if you just want to type that in a calculator and double check, but every single time you have to double check that that value is greater than 0. And if it's not, if it breaks that rule, you have to throw away and it's an extraneous solution. Yes? Cool. So that's what happens when there's a logarithm on both sides. Bases should match, and then you set the arguments equal to each other. What happens, though, if there's only a logarithm on one side? Where the rules are still sort of similar to how they were for exponentials, because all we're going to do, and there's 2 ways we can do this. The instructions here say exponentiate both sides or use the log loop. We're going to use the log loop because that's what we've been practicing with. If you Google that word exponentiate and want to do that method, that's fine. I can show you what it is. But I think the log loop is a little bit more simple. So we're just going to reuse the log loop where we leave the base the exact same and we flip-flop the sides for x and a. Because then we're going to have an x equal to equation, and that's going to be something we can type in a calculator. Now remember though, this is still a logarithm, which means we will have to check the answer at the end, plug it in and make sure it's greater than 0. But that's not too bad. On problem number 9, what is the base? 3. So 3 should still be the base when I flip this. And then I'm just going to switch these two things, which means this is going to be 3 squared equal to x plus 4. We still want to solve for x, but now it turns into an Algebra 1 style problem. What is 3 squared? Don't say 6. 9. So 3 squared is 9, which means I'm just trying to solve 9 equal to x plus 4. We'd take 4 away from both sides to work backwards, and we'd get that 5 is equal to x. We love the log loop. It's just a boop, boop, loop it around. Base stays the same. Now, like I said, though, we do have to double check that the argument is still true. And there's only one argument to check this time, x plus 4. So I just have to make sure that x plus 4 is greater than 0. Is it greater than 0? Yeah, it's pretty obvious. If you have two positive numbers and you're adding them together, it's going to stay positive. But we show that we've checked our work. We know that 5 is a good solution and it's not extraneous. Can you guys try this second example, number 10? You got it. Here, I'll leave it to where you can still see the other work. Do the log loop, solve for x, check your work. When we do this one, we see that the base is 2, and once we log loop it, it would have a power of 3. Well, 2 to the third power is 8, and now I just have a cute little two-step equation to solve. We add 17 to both sides, then divide by 5 to get 5 again. But we check our work just to make sure that that number still stays positive and is greater than 0, and it is. 25 minus 17 is 8, so we're still good, and that is our solution. Does that sort of make sense? Okay, so solving exponentials and solving logarithms seems really complicated because they're more complicated equations than the things we've been working with all year, but I actually think solving them is really quite simple if you just remember that log loop. Now here's something really cool actually. A lot of times students ask, when will we ever use this? No, you might not sit here and write down an equation, but the things you do in real life actually are explained by math. That's why mathematicians mathed in the first place. They wanted to explain the world around them. One of the things that you will probably do in your life is cook something. Yes? Cool. There is this physics law called Newton's law of cooling that is an exponential equation. It's rather complicated at first, but it's really pretty simple once we start using it. It is T equal to T sub 0 minus T sub r times e to the RT power plus TR. But let me explain what all of those things mean. T is your final temperature. So it's cooling, right? You're going to take something out of the oven, let it sit on the counter, and cool off. Does that make sense? We do that, yes? Here's how that happens. Your final temperature is the initial temperature. I'm going to use different color. The initial temperature of the thing you took out of the oven minus room temperature. So the room temperature, the ambient temperature in the room, multiplied by e raised to the RT power. What do we think R is going to stand for? Rate. R in math is usually, a lowercase r like that, especially not in geometry when it can't be radius, is usually rate. And then T is time. So how long do we leave it sitting on the counter? Plus one more time that room temperature. So we're going to use room temperature twice in this equation. Now in this problem, why did I not highlight E? It's a letter. It's a number. So it's always going to be in my Newton's law of cooling because it's a constant number for it that we're going to be multiplying or using the exponent for. So in this example where we will use the Newton's law of cooling, it says Lisa took enchiladas out of the oven and measured the temperature to be 200 degrees Fahrenheit, which means that's the initial temperature of the enchiladas when we took them out of the oven. The room temperature of her kitchen is 70 degrees Fahrenheit. After 20 minutes of letting the enchiladas cool, Lisa measures the temperature to be 135 degrees Fahrenheit. So the final temperature after it has cooled off. The question here is, what is the enchilada's rate of cooling? So what's nice to do with these problems, and I super recommend this if you ever take physics, is you list out all of the things you know. Well, we know that the final temperature is 135 degrees Fahrenheit. We know that the initial temperature is 200 degrees Fahrenheit. We know that the room temperature of her kitchen is 70 degrees Fahrenheit. We don't know the rate, so I'm going to put a question mark right there. But we do know the time. How long did she leave it sitting out for? 20 minutes. So we have everything but one variable. With one variable in one equation, we can solve it. And we just learned how to solve these types of equations. So here we go. We'll set it up. I had to scroll down, but I know you can see the equation yourself. The equation says the final temperature, 135, is equal to the initial temperature minus the ambient temperature, or room temperature, times e to the negative r, I don't know what r is, I'm going to put r there, times t, which is 20, plus 70 degrees, plus my room temperature one more time. There is only one variable in this equation, which means we can solve for it. Now, solving for it is going to be the complicated part, but we've already done this. There is only a variable on one side. So we're going to use the variables on one side rule, which means we just need to be able to get this to be log looped, and we'll be good to go. First things first, let's take care of this parentheses, because PEMDAS tells me to take care of parentheses first. What's 200 minus 70? 130. So I have 135 equal to 130 times e to the negative 20r plus 70. I would need to subtract 70 from both sides because I have to start from the outside in when I'm solving. So I subtract 70 from both sides, but those are like terms, so that works. 135 minus 70 is 65. close to being able to log loop. We have to get rid of that 130. So we would divide by 130 on both sides. And we might have to use a calculator for this one, but what is 65 divided by 130? 0.5. We'll leave it as a decimal because that's a cute decimal. 0.5 equal to e to the negative 20r. Okay, whew, oh my gosh, look at all that algebra. We are now at the point where we can log loop because the base and the power is isolated. So when I do the log loop, what is the base that I'm going to use for this log loop? The base is e, which means yes, I will use the natural log instead of a regular log. So I'm going to put natural log, and then I'm going to flip. I put it on the wrong side, sorry. I'm going to put natural log here, and then I'm going to flip these, which means I should be doing the natural log of 0.5 equal to negative 20 times r. Do y'all still follow the log loop? I just switched their sides, yes? What is the natural log of 0.5? We're not going to be able to do that in our head, but we don't need to use change of base. There's a button for natural log. When you press natural log of 0.5, what do you get? Yeah, I'm going to have to scoot over here because I ran out of room. I'm sorry. We would get negative, approximately equal to, because we rounded, approximately equal to negative 0.693. Have we figured out the rate yet? What do we have to divide by on both sides? Negative 20, yeah. Because then that r is going to be all the way by itself, which is what we wanted. We wanted to know the rate. And that rate is approximately equal to 0.035. Or if we did percentages, that would be 3.5%. Oh my goodness, look at all that algebra we just did. The main idea here is once we get to the point where we had the e isolated, we used that log loop that we discussed. And we were able to figure out the rate at which my enchiladas are cooling. So let's say we were really desperate to eat these enchiladas, but we knew that 135 degrees Fahrenheit, which was the final temperature, was still going to burn our mouth. We need to figure out how long we need to wait to eat our enchiladas so that we don't burn our mouth off. I'd probably eat it at 135 degrees. I like my food hot, but we are going to leave those enchiladas out on the counter, not for 20 minutes, but for 30. How hot are they going to be after 30 minutes? So let's write down what we know. Do we know the final temperature after 30 minutes? No, we're trying to figure that out. So we're going to put the question mark there. What was the initial temperature of these enchiladas? 200 degrees Fahrenheit. My room temperature was still 70 degrees Fahrenheit. My rate, we just found out, is 0.035. And how long are we leaving them out on the counter? 30 minutes. Okay, when we fill this in this time, again, we had one question mark, which means we can solve it. We start filling it in. T for time, we don't know it, so we're going to leave big T right there. It's going to be equal to 200 minus 70 times e to the negative r times t plus our room temperature. It's gnarly to fill it in, and I'll give you a second to catch up to me. But once we fill all of this in, do you notice something really nice about all of the things on the right side of the equal sign? We have all the variables. Everything is a number, because remember, e is a number, which means if you use your parentheses right, you just type that thing in a calculator. You press go, which is what we're going to do. So we go to our calculators, and we say, open parentheses. 200 minus 70, close parentheses. Ooh, I need E on my calculator. Where is E on your calculator? Yes, second and then divide gives you the E. Then I'm going to go up into exponent world and type negative parentheses 0.035 close parentheses open parentheses 20 close parentheses. Get out of exponent world plus 70. Y'all gotta stop me when I do something silly. I used the wrong time. I put 20. How many minutes should it be cooling? Yeah, my bad. When we press enter, what do you get? 115 point, I get 491 degrees Fahrenheit. So sometimes these cooling problems are complicated like the first one we did where we had to solve a whole bunch of things. And sometimes they're really pretty simple because you plug everything you have in and then you get a final temperature of your food.
Do you have to use 200 minus 70?
Yes, you do have to use the parentheses with 200 minus 70. I always recommend if you've written a parentheses on your paper, you write a parentheses on the calculator, like 100%.
I got 240.